Good afternoon, everyone. Today we'll discuss about the law of conservation of momentum or the equation of linear momentum equation or else balance of linear momentum equation. As or else in the exam they may ask that derive the Navier Stokes equation. In that case, we have to derive the today's expression. So we'll study what the statement. The equation of motion are derived from the Newton's second law of motion, which states that the rate of change of linear momentum is equals to the total force. Let us name this as a equation number 1. So in order to prove this statement, we have to consider an enclosed surface as having its volume as V at a time t seconds. Now the rho is a density function of xyz as well as the type rate, and q is the velocity of the fluid particle which is moving in a enclosed surface. Now by the definition of linear momentum, which is indicated by m, it is given by product of mass into velocity. So momentum is nothing but a product of mass into velocity. So mass can be written as rho into dv and q is nothing but a velocity. Let us name this as equation number 2. Now, in continuum mechanics, two different types of forces are acting on a body. So, one is a body force and another is a surface force. Body force is nothing but a force acting throughout the body of the body is known as a body force. Force which acts on every element of a material and hence on the entire volume of the material. One of the best example is nothing but a gravity force, which acts on our body. Okay, mathematically we can write the body force as rho into b into dv, integration over v, rho b into dv, where b is nothing but a body force per unit mass and hence the dimension force per unit mass can be calculated. Now, and surface force is nothing but a force acting on a surface of the boundary, that is indicated by Fs. And mathematically we can write the surface force as S into ds. Now, in order to write the resultant force, what we are doing is we are adding sum of the body force and the surface forces so that we can get the resulting forces Fr. Now, we substitute this value in the first statement. First statement tells that law of conservation of moment, that is rate of change of linear momentum is equals to the resultant force. So the rate is nothing but d by dt of m, that is equals to Fr. Okay. Now substitute the value of m, Fb, Fs. Okay, you will get the equation number 7. Interchange the place of integration and the derivative so that you will get integration over v rho into dq by dt into dv. This is equals to integration over v rho b dv and integration over s dot ds. Now, by the Cauchy principle, which connecting about the stress vector and the stress tensor, that can be written as rho of n equal to t dot n. We will use this concept for our integration. The integration over s dot ds, this is equals to integration over s t dot n into ds. Now convert this integration over the surface into volume integration by using Gauss divergence theorem so that we can write divergent of t. So now you substitute this value in your equation number 8. Now and bring all the terms to the left side so that you will get integration over v rho into dq by dt minus rho b minus divergence of t into dv. This is equals to 0. This holds since the integration is taken, volume is taken arbitrarily, so that this integrand get vanishes. So when it get vanishes in the sense, we'll get only the term containing rho dq by dt minus rho b minus divergence of t. This is equals to 0. This holds for every point in the fluid at any time. Now, this equation 10 is known as a principle of balance of linear momentum in terms of Cauchy stress tensor, and this was first introduced by Cauchy in 1827, and this equation is known as a Cauchy's equation of motion. This can be written in component form also, that is given by equation 11. Further, equation 10 can be represented by taking the substitution of the Stokes law, that is T equals to minus P plus lambda grad dot Q into I plus mu into grad Q plus grad Q transpose. Now apply grad on both sides so that you'll get divergence of T. This is equals to grad of minus P plus lambda grad dot Q plus mu times of grad dot grad Q will be grad square Q plus the here it is grad of grad dot Q. Now substituting equation 13 in your 10th equation, and we'll get the equation like this. It is rho dq by dt equals to rho b plus grad minus p plus lambda grad dot q plus mu grad square q plus grad of grad dot q. Now what we are doing is we are arranging the terms in such a way that the pressure term we are writing first and the body force second and the viscous force third and the remaining term that is lambda times of grad dot q and here mu of grad dot q. Here among these two grad q is common. The leftover term is nothing but lambda plus mu. Lambda and mu, they are nothing but viscosity coefficients. And this equation 14 is known as a general form of equation of conservation of linear momentum for viscous fluid. For if the fluid is incompressible in such cases, grad dot q equals to 0. As you know that incompressible fluid in the sense the density is constant. So here this 14th equation, the last term get vanishes. You left over with only the term containing rho dq by dt equals to minus grad p plus rho b plus mu grad square q. Here dq by dt by the help of local and individual time rate of change relation. Further we can split this as dq by dt plus q dot grad q. This is equals to minus grad p plus rho b plus mu grad square q term. Here, this is a local acceleration term, and q dot grad q is nothing but a convection term, and this is a pressure term, and rho into b is a body force, and mu into grad square q is nothing but a viscous force. So this equation 15 is known as a law of conservation of momentum or Navier Stokes equation.